Okay, we're going to have a little look at differentiation. Now, as I said, the video that we had online didn't look or go into quite the same level of explanation or detail as I wanted. They were either just too complicated, not complicated enough for my liking. So what we're going to do is we're going to take a look at differentiation. Now, this is an introduction to calculus, and you'll notice that it says there quite clearly differentiation, gradient functions, that's what that says. And differentiation is all about the gradient. That's what we're going to be looking at, it's what we're going to be working with. So where have we met gradient so far? Right. The gradient that we've met so far, okay, has been to do with straight lines. So what is this thing called differentiation? Okay, well, we're going to look at what it is, how to do it, and we're going to look at the relationship between the gradient of the curve and the gradient of the line between 2 points on it, and how this leads us to differentiation. Okay, and then finally we're going to work on using and applying differentiation. So the gradients of lines. Now we know that we can measure the gradient of line, and we can actually work out the gradient of any line if we've got the equation of the line. So the equation of the line is y equals mx plus c, and if we identify the value of m, like the plus 6 that's here, we can say that this line now has a gradient of 6. So if we've got an equation like 2x plus 5y equals 4, this could be written as 4/5 minus 2/5 of x, telling us that the gradient is minus 2/5. Yeah, so we can quite easily identify the gradient of a line by looking at the coefficient of x. But what about curves? Well, curves are a lot more complicated, because the first problem we have with curves is, well, their gradient's going to change all the time. They don't have a fixed amount of steepness. If you remember, that's what the gradient's all about. It's about how steep something is. So, if we think about curves, and here we have a diagram with various nodes on, let's just have a little look at an example which is more general and a bit clearer. We have a curve. Now, the curve up here is actually quite steep, but as we come further down the curve, the gradient gets less steep, but you can see we're still pointing downhill from left to right. We still have a negative gradient going downhill from left to right, but it gets less and less steep until right down here at the bottom it's actually flat. There is zero gradient down at the bottom. If we then carry on going upwards, you can see that we start to get a positive gradient, and that the curve continues to increase in steepness. It gets steeper and steeper and steeper as we go along. What differentiation does is it looks to link the equation of a curve to the equation of its gradient, or to a formula for its gradient. So here we've got the equation y equals x squared. Now if I just use autograph for a second here, I can put a tangent to the curve in. Okay, it's any one of these points. So carrying on round, I'm going to put a few more tangents in and see what we get. So I've put four tangents, on that graph. One at x is minus 2, one at x is minus 1, one at x is 1, and one at x is 2. The graph is y equals x squared. So let's put some information about these up on the board. So first we have this one. Now this one is the tangent y equals 4x minus 4. This is the tangent minus 2x minus 1. Okay, this is the tangent 2x minus 1. finally we have this tangent just here. So it's the tangent y equals 4x minus 4. So by looking at the four tangents, we can see that when x was minus 2, we had the tangent y equals minus 4x minus 4. When x was equal to minus 1, we had the tangent y equals minus 2x minus 1. And when x was equal to 1, we had the tangent y equals 2x minus 1. And when x was equal to 2, we had the tangent y equals 4x minus 4. Now the gradient of the tangent tells us the gradient of the curve at that point, because the definition of a tangent is it's a line that passes through a particular point on a curve and shares the same gradient as the curve at that point. So I can see that when x is minus 2, the gradient of the curve is minus 4. When x is minus 1, the gradient of the curve was minus 2. When x was 1, the gradient of the curve was 2, and when x was 2, the gradient of the curve was 4. So here's that information put onto the graph of y equals x squared and joined together. Now if we look carefully, we can see that there's actually a connection in the gradient of the tangents at the various points, and therefore the gradient of the curve, and the x-coordinate that I do them at. So when I did a tangent at x equals minus 2, the gradient was minus 4. When I did a tangent when x was equal to minus 1, the gradient was minus 2. And we can see that what's happening there is that every time we want to work out the gradient of the curve for a particular x value, the gradient is twice as much as the x value. Even when x was equal to 0, the tangent would have been this horizontal line y equals 0, 0 gradient, 2 times 0 is 0. So let's extend this idea. There is, and I'm telling you this, there is a connection between the rule which starts y equals, so in that case it was y equals x squared, that tells us where do we plot the y coordinates based on the x coordinates, and the gradient function. So, the process of changing a y equals rule into a gradient function is called differentiation, and the outcome is called the derivative. The gradient function is denoted with this notation here, dy dx equals. So this dy dx is like one big piece of notation that means the gradient function is. So what we're going to do now is we're going to take some of those rules, some of those ideas, and we're going to build things up. Now normally in lesson I do this with whiteboards, but we're doing it kind of via video now, so we're just going to have to try and think things through. So I'll leave things up for a little bit, you can try and write them down, see if you get them right, see if we establish the pattern. So we already know that when y equals x squared, the gradient function dy dx is equal to 2x. So when y is equal to x squared, if we want to work out what the gradient of any coordinate on y equals x squared is, we can use this formula, 2x. So the gradient function is 2x. Okay, so if x, the coordinate for x is equal to 4, then the gradient would be equal to 8. If the coordinate for x was equal to 5, then the gradient would be equal to 10. If the coordinate for x was equal to minus 7, the gradient will be minus 14. So, how do we do it for y equals 2x squared? Well, different people have different ideas at this stage. Some people say, well, maybe it's just 2x again. Some people correctly tell me that the answer is y equals 4x. And that makes sense, really, because if you think about what happens when you've got the graph of y equals 2x squared, the whole thing gets stretched twice as long in the y direction. It gets steeper. In fact, it gets twice as steep. So obviously the gradient that measures steepness is going to be twice as big. So for y equals x squared, the gradient was 2x. So for y equals 2x squared, the gradient function is twice as much as 2x. That's 4x. Right. For y equals 3x squared, what's the derivative? What do we think the derivative is going to be? Let's just take a couple of seconds to think about that. Okay. See if your guess matches what's correct. So the gradient function is 6x. That kind of makes sense again because it's 3 times steeper this time, so the gradient function is 3 times as much. Let's try another one with x squares. So if y is equal to 5x squared, what do we think the gradient function is? Hopefully, you wrote 10x. 9x squared, what do we think it will be? 18x. So any number times by x squared, what's the connection? Well, the connection is that whatever number it is, it's double that number times x. So what happens if we increase the power? What happens if instead of having y equals x squared, we want to have y equals x cubed instead? Now when I do this in lessons, we tend to get a few guesses now. Give yourself 10 seconds to write down a guess. I'm not expecting it to be right necessarily, but have a guess. Right. The guesses I tend to get at this stage are that dy dx is equal to 3x, or the correct answer, dy dx is equal to 3x squared. So let's just think about what we've got there. We had this kind of, I can see logically where both of these ideas come from. This one just says, well, I'm timesing by the power, whereas this one timeses by the power and reduces the power by 1. So this is the correct answer. That's what we should have get. So let's try a few more with x cubed and see what else we discover. So if y is equal to 2x cubed, what do you think the gradient function is going to be? So for y equals x cubed, it was 3x squared. What do we think it will be for 2x cubed? The answer is 6x squared. So just like with y equals x squared, if we double the function, we double the gradient function. So what's it going to be for 5x cubed? That's right, we're going to get 50x squared. For 10x cubed, x squared, 7x cubed, 21x squared. Any number times x cubed. Okay, we're going to multiply it by 3. So you'll see what's happening this time is that we are multiplying by the power, and that the power is changing from x cubed to x squared. Let's have one more example worked through before we kind of look to generalise the process. So y equals x to the power of 4. That gives us 4x cubed. So you can see that we've got this similar process going on, that we've got the power coming down and multiplying the whole function, and that we've got this change to the power. So if y equals x to the 4 becomes 4x cubed, what do you suppose is going to be the answer for y equals 2x to the power of 4? That's it, the answer is 8x cubed. 5x to the power of 4? The answer would be 20x cubed. 9x to the 4? 36x cubed. So hopefully we can see now that there's a formula appearing. It's that any number times by x to the power of 4 becomes 4 times that number times x cubed. So what would we say would be the general process for any number multiplied by x to the power of any integer? So differentiation in general. Let's give you 10 seconds to think on that. There's the answer. The general formula for differentiating a multiple of a power of x is that we times by the power and take one away from the power. So we timesing by the power and taking 1 away from the power. Times by the power, we take 1 from the power. Some people prefer to think of it in words, some people like seeing it in algebra. All that matters is that you know how to do it, and of course, what it's finding. It's finding a function for the gradient, a rule into which we can put numbers to find out what the gradient is. So, this leaves maybe a couple of questions. What do I do if there isn't a power? If there's no power on the x, so we've just got 2x. Well, the answer to that is we think of the 2x as being 2 times by x to the power of 1. Now, 2x to the power of 1, we times by the power, we times by 1, well that just leaves things unchanged. We then take 1 from the power, leaving us with x to the 0. Now from our GCSE studies, we know that anything to the power of 0 will give us the answer 1. So therefore we've got 2 times 1, which is 2. So for any number times by x, the derivative is just the number, and that works for anything. So I could have minus 3x. The derivative will be 3. Minus 3, so if I could have pi times x, the derivative, the gradient function, would just be pi. So what about numbers on their own? Well, if we've got 3, and we look at this line up here, we said 2 could be thought of as 2 times 1, which is 2 times x to the 0. Applying that same kind of logic, that 3 could be thought of as 3 times 1, which is 3 times x to the 0, we could consider ourselves to be timesing by the power of 0, and then we end up with nothing. Well, nothing times anything is nothing, isn't it? So we're left with nothing at all. And that tallies up with what we've seen already, because at the start of the lesson we said if y was equal to 5x minus 4, it was a straight line, then the gradient is equal to 5. And that kind of works. If we've got y equals 5x minus 4, dy dx says, okay, any number times by x just becomes the number, so that's 5. And any numbers that we've got tagging on the end there, well, they just kind of disappear, they just go away. So it'd be just 5 and nothing, so 5. So the final thing that we need to deal with is what happens if we've got lots of terms? What happens if it's more than just one term, like 5x squared, 3x cubed? Well, the answer is that we just differentiate every term on its own and go through the function in that way. So if y was equal to 5x cubed minus 2x squared plus 4x minus 3, dy dx is going to be equal to 15x squared minus 4x plus 4. Remembering that we're timesing by the power and taking 1 from the power. Timesing by the power, taking 1 from the power. Numbers times by x just leave us with the number. Numbers on their own disappear. Take some time just to try working out this one. So what did you get? Answer is, let's have a look. Timesing 7 by the 3, we get 21. Taking 1 from the power, we get x squared. Timesing the 6 by the 2, we get 12. Taking 1 from the power, we get x. Any number times by x just leaves us with the number. Any number on its own disappears. 21x squared plus 12x minus 9. Got a whole page of examples to try here. You'll note that some start with y equals, some start with f of x, some just being expressions, but we can technically differentiate any of these. The only thing that really changes is our notation. If we've got y equals notation, we should end up with dy dx equals as our gradient function. If we're starting off with f of x as our notation, then our gradient function is denoted, are you ready? F with a little dash, like that, f dashed of x. Okay, for this kind of problem, where you haven't got y equals or f of x, what you'll quite often see written is d dx, and then a bracket, and then the function. Obviously that takes quite a bit more writing. That's what you'll see. Now, feel free to pause this slide, have a go at some of these questions if you feel like you need a bit more practice with the process of differentiation. Otherwise, we're going to move straight on to an example. So feel free to pause this, try these, get some ideas. I'm trying to stick some answers up somewhere, possibly in the email I'll send out to you. And then we'll move on and do an example. Right, so using this idea. So it's all well and good being able to find the gradient function. It's much more useful to be able to actually do something with it. So how would we use this? Well, here's one very straightforward example. Find the gradient of the curve y equals 5x squared minus 6x plus 2 at the point when x is equal to 7. How do we do it? Well, you can see that the question wants me to find the gradient of the curve. Now, in this format, this equation doesn't tell me anything about the gradient. At the moment, what I've got is a formula that says if I put an x coordinate in here, I'll tell you where the y coordinate is. So in order to make that function tell us about the gradient, what we need to do first is differentiate it. We need to find the gradient function. So taking this function and working out dy dx, what do we get? So dy dx is going to be equal to, well, we times by the power, that's 10. We then take 1 from the power, so that's x to the 1. As we saw earlier, any number multiplied by x is minus 6. This one is its number itself, just becomes the number. Any number on its own actually just disappears. So dy dx for this function is 10x minus 6. So now to find the gradient at the point when x is equal to 7, I just go if x equals 7, dy dx equals 10 times 7, take 6, which is 64. And that is the gradient of the curve y equals 5x squared minus 6x plus 2 at the point